CCI, Crash Course Instrumentation, presents Saturday History Special, April 17. A short history of sensors, from metal junctions to MEMS. Goal: tell the origin story of the sensors we use every day in plants and labs. Cold open: every great measurement started as a wild idea. Today we race from 1800s metal junctions to modern micromachines you can barely see. 1. Early clues, 1800s, light, heat, and magnetism. 1821. Thomas Johann Seebeck notices that two unlike metals joined at one end and held at different temperatures generate a tiny voltage. This thermoelectric's insight births the thermocouple, prized because it works at extreme heat and needs no power. 1873. Willoughby Smith finds that selenium's resistance drops when illuminated while testing undersea telegraph cables. This photoconductivity discovery leads to early light meters, phototubes, and eventually common photodiodes and solar cells. 1833, 1843. Samuel Hunter. Christie proposes the resistance bridge. Charles Wheatstone popularizes it and refines the null measurement technique. The Wheatstone bridge becomes the backbone for reading tiny resistance changes in one strain, a temperature, and one light. Sensors with precision. 2. From lab curiosity to industrial workhorse, late 1800s, early 1900s. 1879. Edwin Hall observes charge piling up on one side of a conductor in a magnetic field. The Hall effect enables contactless, speed, and Hall position, sensing and later powers, brushless DC motor, commutation. 1899, 1920s. Callender and Van Dusen map platinum's resistance versus temperature with equations you still see in spec sheets today. This turns Plankton's platinum RTDs to reliable, calibratable thermometers for industry and labs. 1887, 1921. Heinrich Hertz first observes the photoelectric effect. In 1905, Albert Einstein explains it, and later wins the 1921 Nobel Prize. Understanding light-driven electrons leads to better sight phototubes, photodiodes, and light-based controls. 1928, Hans Geiger and Walter Müller build a robust counting tube. The Geiger-Müller detector makes ionizing radiation audible and countable, critical for safety where medicine and physics. 3. The 1930s. Boom. Precision, motion, and materials. 1938. Edward Simmons, Caltech, and Arthur Ruge, MIT, independently invented the resistance on strain gauge within weeks of each other. Bonded foil grids wired in. Wheatstone bridges. Unlock accurate measurement of some force, weight, pressure, and stress in structures. 1930s. The LVDT, linear variable differential transformer, emerges as a frictionless position sensor using a movable magnetic core and transformer coils. Clean AC signals and infinite resolution make it a favorite for servo systems and harsh environments. Commercial units follow in the 1940s. 1930s. Thermistor enters the vocabulary as ceramic, NTC, devices become practical. Huge resistance change per degree gives superb sensitivity for thermostats, inrush limiters, and precision thermal control with math to linearize. 4. Silicon changes everything, 1950s, 1970s. 1954. C.S. Smith reports the piezoresistive effect in silicon and germanium, orders of magnitude larger than metals. Suddenly you can pattern pressure, force, and bond acceleration. Sensors right on a chip. 1960s, 70s. Thin film processes and better packaging standardized platinum, PT100, and Bosobund P1000, RTDs for industry. Stability and repeatability make them calibration anchors. 1970s. Fiber optic. Sensing matures. Interferometers and Bragg gratings measure strain, temperature, and vibration through light. Immune to electromagnetic noise and safer in explosive atmospheres, fiber finds niches in power, oil and gas, and civil structures. 5. Micro-machines and the sensor everywhere. 1990s today. 1991. Commercial. MEMS. Accelerometers like the ADXL50 put a full inertial sensor on a chip for automotive airbags. That price-performance wave spreads to bikes, phones, drones, and mass industrial diagnostics. 2000s today. MEMS goes wide. Gyros. Magnetometers. Barometric pressure. Microphones. And chemical sensors, often fused in software, to give reliable, low-power measurements. Today, smart, networked, and safe. 4 to 20 milliamp, loops with heart, overlays, full, field bus, and intrinsically safe. Designs push trustworthy data across noisy plants. Why this matters? Better sensors made feedback control possible. Quality improved, waste fell, safety rose, and plants became more predictable. Trade-offs never went away. Speed versus stability, sensitivity versus durability, cost versus accuracy. Engineers still balance these on every project, oddities and weird wins, short stories. Cosmic static versus pigeons, 1960s. Radio engineers chasing mysterious microwave noise finally traced part of it to pigeons roosting, and their dielectric droppings in a horn antenna, then went on to help confirm the cosmic microwave background. Lesson: clean your sensor before rewriting physics. The theremin, 1920s. A musical instrument you play without touching, using capacitive proximity, sensing from your hands. It's a wonderfully weird ancestor of today's capacitive touch and level sensors. Biological sensors in mines, 1800s, 1900s. The town canary in a coal mine was a living gas detector for carbon monoxide and other hazards, crude but effective before electronics. Crowdsourced seismology, 2000s. Networks that tap, laptop and smartphone accelerometers. Proved you can detect earthquakes with millions of tiny, cheap sensors. An early taste of the Internet of Things for science. Wrap up, what to remember. Thermocouples, started with heat-made voltage. RTDs, thermistors, turned heat into resistance. Strain. And LVDT, captured motion. Hall, red magnetism. Piezoresistive silicon. And MEMS, shrank it all to chips. Fiber optics, brought light into the mix. Bridges and signal conditioning made tiny changes readable. Modern sensors are cheaper, smaller, and smarter, but the physics roots are the same. Credits and CTA. Thank you to Tony Coupault and the open source community for the models and inspiration behind Crash Course Instrumentation. If this helped, please like the video, subscribe to Crash Course Instrumentation, and share with a student, coworker, or your plant's apprentice.